the amount of HCl that's produced by those parietal cells ends up leading to a very low pH. The stomach has a pH of less than 2. It's usually around between 1.5 to 2. And that pH, that very low pH, has a few key functions. We've already mentioned that it helps to kill a lot of the bacteria that we ingest, but it also does some other important things. It causes proteins to denature. We're familiar with this. We had a lab on this earlier in the semester. We can use heat to denature proteins, or we can use low pH. We can use acids to denature proteins. So this is one of the key things. It causes proteins to unfold, and then that allows enzymes to have access to the peptide bonds. And the enzyme that is involved in protein digestion is pepsin. So this brings us back to the chief cells. We said chief cells are producing pepsinogen. Okay, pepsinogen is the precursor for this enzyme. So what happens is pepsinogen molecules, they actually act on each other. They partially digest each other, and as a result, they end up cleaving off small, sort of like inhibitory fragments. They cleave those off, and then the net result is that the pepsin enzyme is now in its fully active form. So in low pH, pepsinogen acts on others like itself in order to form the active form of pepsin, which can then initiate digestion of proteins. So that low pH is key for allowing protein digestion to start. Once pepsin is produced, it has an optimal pH range. Remember, all enzymes do. Pepsin's optimal pH range is right about pH of 2, so this helps pepsin to work very effectively in the acidic environment of the stomach. This acidic environment inactivates other enzymes. Remember, we said in the mouth, salivary amylase starts the digestion of starch. That's an enzyme that's optimal pH is basic, is not basic, is neutral, so pH of 7. And once that enzyme is now here in the stomach, it's going to be inactivated. So starch digestion is put on hold for the time being while in the stomach, and then starch digestion will continue once we make it into the small intestine, where it's not quite so acidic anymore. As far as digestion goes, there's not really a whole lot of digestion taking place in the stomach, just proteins. Proteins are being digested. Carbohydrates and lipids are not digested in the stomach. They just kind of hang out until later on in the digestive tract. Most of digestion is going to take place in the small intestine once the chyme enters the small intestine. And there's an interesting sort of aside from this. This means that people who have their stomachs removed, it's called having a gastrectomy, people who have their stomachs removed, they can actually still digest and absorb nutrients from food without much trouble. They of course have some modifications to their dietary needs, but digestion can still take place because the small intestine is the key place where that happens. The one thing that is absorbed by the stomach is molecules that have high lipid solubility, and that includes things like alcohol and also some drugs, non-steroidal anti-inflammatory drugs like aspirin and ibuprofen. Those are substances that can be absorbed through the stomach, and this can end up leading to damage of the lining of the stomach. This can lead to bleeding if these substances are used long term, so that's why it's important for use of them to be in limited amounts. Given that the pH of the stomach is so low, and given that pepsin has been activated to digest protein, why doesn't the stomach digest itself? It's a good question to ask. There are a few key reasons, a few key defenses that the stomach has to protect itself. We've already mentioned the tight junctions that exist between the epithelial cells. That helps to prevent the acid and pepsin from making its way in between cells. But there are still those surfaces that are facing the lumen of the stomach. Why don't those surfaces of the epithelial cells get degraded over time? So a couple of other things that come into play. The mucus that is produced, the mucus in the stomach actually has a lot of bicarbonate ions in it. And it's a mucus that's particularly sticky. It tends to stick to the epithelial cells. So that helps to provide a basic lining to the stomach, which neutralizes the protons that come in very close contact with it. So that's very key, that's very important. And then the other thing that takes place is that the epithelial cells get replaced approximately every 3 days. So these cells undergo high rates of division. Mitosis is happening frequently, and so that helps to replace any cells that might be starting to be damaged due to exposure to acid and pepsin. Sometimes HCl does manage to erode sections of the stomach mucosa, and also in the first section of the small intestine. Sometimes this can happen, and this is what an ulcer is. A peptic ulcer is a spot where there has been damage due to these substances. So with ulcers, many people who have ulcers also have a certain type of bacterium living in their stomach. It's called Helicobacter pylori. The presence of this bacteria doesn't necessarily cause the ulcer, but it can contribute to it. So the presence of this bacterium tends to reduce the mucosal barrier, and so it makes a person more susceptible to damage. Usually treatment for ulcers involves a couple of key things. One is just to help decrease the amount of protons that are being secreted into the stomach, so it raises the pH a little bit. But also treatment with antibiotics, it tends to be a helpful combination treatment approach. So treating for this type of bacteria will lead to a stronger mucosal barrier in the long run. And again, we've already mentioned that there are some substances that can damage the mucous membranes. Overuse of non-steroidal anti-inflammatory drugs. For some people, this is hard to avoid. This is a hard balance. They might have a good reason for taking like ibuprofen for inflammation control, but using it too much can lead to problems in the GI tract, in the stomach specifically. So that can be a balance, a challenging balance for some people to achieve.